The law of electrostatic attraction says that opposite charges attract and like charges repel. If we have two different charges, positive and negative, they'll tend to attract each other. If we have two identical charges, a positive and another positive, they tend to repel. Same with negatives and other negatives, they tend to repel. This is also called Coulombic attraction. In the 1870s, William Crookes, who had a killer mustache, discovered that rays caused a shadow when they were emitted from a cathode, which is why old school televisions, old school computer monitors, radar screens that you might have seen in movies from an earlier day are called cathode ray tubes. This bit here in this picture on the right, that was the cathode, and it turns out that there was this little Maltese cross, and it would form a shadow on the back of this glass tube that was evacuated of air. He didn't know what was causing the shadow, but he called them cathode rays because they emanated from the cathode and were blocked by the cross. In 1897, J.J. Thompson discovered that Crookes' cathode rays were deflected by electric and magnetic fields. He found that the cathode rays were particles. Today we call them electrons, and they have a certain charge to mass ratio, and it's given there. So Thomson's apparatus kind of looked like this. He had a cathode ray tube similar to what Crookes used. Over here we had a phosphorescent screen that would glow when hit by these cathode rays. So there would be this nice, let's say, greenish glow right there. And what Thompson did was put an electric field across the cathode ray tube, which gave one plate a negative charge and the other plate a positive charge. In other words, there was a voltage difference. There's an electric field now between these two plates. And if these cathode rays are simply light, they will continue to travel in a straight line, because that's what light does. Light is not affected by electric fields. And what Thomson found was that the cathode rays deflected. They tended to veer a little bit towards the positive plate and away from the negative plate. And based on that, Thomson concluded that these cathode rays weren't like rays of sunshine. They were actually particles, and that they had a negative charge. And he was very clever enough to figure out the charge to mass ratio of those particles. Although he didn't find the charge and he didn't find the mass, he did find the ratio. We call cathode rays today electrons. Then, since the atom was known to be electrically neutral, Thomson proposed his plum pudding model. In other words, if there are negative particles, and we know that the atom is neutral, then there also must be positive particles. And since it was known that the positive particles were much more massive compared to the negative particles, Thomson imagined little tiny negative particles embedded in a much larger mass of positive particles. And that's why we call this the plum pudding model. If an American had come up with this, we might call it the chocolate chip banana bread model, where the chocolate chips are the negative particles and banana bread is the positive portion. Milikin helped us with our next step, identifying some more characteristics of atoms. He performed an oil drop experiment. Oil drops were given negative charges of varying magnitude. So here was his apparatus. Notice that on the left we have a battery attached to the plate at the bottom and a plate at the top. And there was a little hole right here in that plate. And in this atomizer, in the upper left, there was oil. And you would squeeze this bulb, and little tiny droplets of oil would come out into this upper chamber. And of course, because of gravity, they would fall, some of them would fall, through this hole. Now, these particles were given a charge. using X-rays, and because they were charged, then they would be attracted or repelled from one plate or the other. And so what could happen is a particular oil droplet could be made to hover in front of this microscope right there. So this oil droplet, Milikin could focus on this oil droplet and he could make it just hover there with gravity pulling it down and the electric field holding it up. There's a free body diagram of one of these oil droplets that is hovering motionless in that chamber. If you've taken physics, you know that the weight of the oil droplet can be found by taking its mass times the acceleration due to gravity, and the upward force can be found by the charge that's on the oil droplet multiplied by the electric field. So those forces are equal for any oil droplet that is motionless. We know the acceleration due to gravity. We can look through the microscope and we can measure the diameter of that essentially spherical oil droplet. And if we could measure its diameter, then we know its volume. And if we know the volume and the density of that oil droplet, then we can calculate its mass. So in other words, the entire left side of this equation we know. We also know the magnitude of the electric field because we have set that when we have charged these plates. We have a little dial and we've set what the magnitude of the electric field is, which means we can calculate Q. And Milikin did this for many, many oil droplets. And these are some examples of numbers that he came up with. So one time Q came out to be 4.8 times 10 to the negative 19th, and 3.2 times 10 to the negative 19th, 8 times 10 to the negative 19th coulombs. And it turns out that those are all multiples of this number, 1.60 times 10 to the negative 19th coulombs. Milikin reasoned that this must be the charge on a single electron, because some of those oil droplets would have lost one electron, some would have lost two, some would have lost 3, 4, 5, 6, and so on, which is why all of those charges that he calculated were multiples of this 1.6 times 10 to the negative 19th coulombs. So Milikin found the charge on a single electron, and then because Thompson previously had figured out the charge to mass ratio, Milikin was able to calculate the mass. Milikin found the charge on a single electron. Thompson had found the charge to mass ratio, and Milikin therefore found not only the charge on an electron, but also its mass, or its rest mass. Thompson modified Dalton's model of the atom when he realized that atoms contain smaller subatomic particles, some with a positive charge, and electrons with a negative charge. Thus, Dalton's solid blob model gave way to Thompson's mushy squishy plum pudding model. J.J. didn't figure out either the electron's charge nor mass, but did find its charge to mass ratio. And secondly, in his oil drop experiment, Milikin was able to determine the charge on an electron. Then, from Thompson's charge to mass ratio, he calculated the electron's mass.